Welcome to this lecture on applied statistics. Today we will give an overview of non-parametric statistics. We will cover chapters 16, 1 to 4 in this book by Walpole, Myers, and Ye. To start off, let's recall the situation in two-sample analysis where we have samples from two populations, and we say that the first population, maybe this one, is x1, x2 up to xn1. The second population, in this case it's two different materials that are measured, is denoted y1, y2, yn2. The interest in these two sample situations is to test whether one group is different from another, perhaps checking if the mean of the two populations are the same or if the variances are the same. And when this is done, one is typically assuming a distribution for these samples. So we might say that, okay, these samples are IID, independent and identically distributed, and they are also normal distributed from a mean mu1 and a variance sigma 1. The second population might have the same, but then it's mu2 and sigma 2 squared. And when we then test mean values, we check if mu1 is equal to mu2, or we can check if the variances of the two groups are the same. And if we do these standard assumptions of normal distributions, we do parametric assumptions. And this is fantastic because it gives us all this machinery of normal distribution. We can have test statistics there. T-distributions, we can do t-tests, either with pooled variance estimates or in other ways. And we can also test variances with chi-square distributions and then Fisher distributions. It's all very nice. But then again, it relies on this parametric assumption of the normal distribution. And sometimes we don't want to do this. And that's when we are in the non-parametric setting. Here, we would have a minimum number of assumptions on the sampling distributions of different groups. And then you might say, okay, is this important? Under the central limit theorem, if we start taking means and averages, things converge to the Gaussian distribution. But maybe we have small samples, or maybe it's not so easy to estimate the variance, so we don't get these t or chi-square distributions as easily as we hope. So then non-parametric statistics is about putting a minimum number of assumptions into a distribution. The simplest such test that we will use first to motivate the setting is the sign test. And this sign test is for the median of the distribution, so it doesn't even have to be a symmetric distribution here. There are very few assumptions on the distribution. Under the hypothesis, in a single sample setting, so no two sample setting here, in a single sample setting, we have a hypothesis saying that the median is equal to some specified value, mu0 tilde. Under the alternative hypothesis, we say that, okay, the median is smaller than this specified value, or it could be bigger, or even a two-sided test. To conduct this test, we will actually look at the samples, and that's it, and check if the samples are below or above this specified median. And since the median splits the sample in 50-50%, this should be more or less equally distributed. We should have about the same number of samples below as we have above the median. So it's a relatively simple test of just counting the data above and below mu tilde 0. So here is our test statistic in this situation. We count the number of data samples that are above the median, the specified median. So here the indicator is defined as a 0 or 1 variable. And it's 1 if the data sample is above the specified median, and if the data sample is below or equal, it's defined as 0. And if you recall such indicators from statistics or probability theory, you might recall that this is the definition of a binomial distribution. Then you have a number n of independent trials, and in each trial you have the same success probability. In our context, with a pre-specified median of mu tilde 0, the success probability is a half. Because under this hypothesis H0, we are equally likely to end up on the left side or the right side of mu tilde 0. So that's why we get the probability a half here. So now under the hypothesis H0, we know the sampling distribution of X, and this means we can do hypothesis tests. We can then compute, for instance, p-values, where we look at the probability of observing such a small or large value of X. Is this subject to random variation, or is it substantially larger or smaller than we would expect under the hypothesis? So that's how the sign test works. And let's go through this in a simple example. In this one, we have 11 data sets, 11 data samples, and we have a hypothesis saying that the median is here 1.8. In our data set, there's actually one value that is 1.8. So this is not below and not above, and we will remove this one from our sample when we do the sign test. And then we will count, okay, where do we have values that are below, and where do we have samples that are above? So we can sketch this on a line. Here is mu tilde 0, which is 1.8. And then we look at, okay, are we on the plus side or are we on the minus side? And then we go through here. 1.5 is the first one, 2.2, 0.9, 1.3, 2.0, 1.6, 1.5 again, 2.0 again, 1.2, 1.7. So we see that there are 3 samples here and 7 samples on the downside. So that means X, the sum of these indicators that are larger than 1.8 is here equal to 3. And the question is then, okay, is this too small? Or is this something we would expect when it's random, if a sample comes above or below 1.8? And this is relatively easy to compute from the binomial distribution. We can put up the binomial probabilities, which are sketched in this diagram, and then we compute the p-values of observing something as small as 3 or smaller. And since this was a two-sided test, we can also look at the other side. What would be the chance of observing something that extreme in both the lower part and the upper part? So here we see, okay, if we look at 3, we get this one, this one, this one, and this one. That's the sum of these is the probability of being 3 or smaller. And the binomial is symmetric around 5, since we have probability 1/2. So we can also look at these probability at the 7 and up end. And doing so, we get a very large probability, much larger than the significance level that we use to do the test. So this is not very surprising. And this means that we would not reject the hypothesis. Having 3 samples and 7 samples on the 2 sides is not very extreme. That happens often. As you see, the sign test is quite easy to perform. You just count plus and minus relative to a specified value of your test. And then you can look up the binomial distribution. So there are also other ways of doing this. If you do not want to do binomial computations, there is a normal approximation to the sign test. And this holds very accurately because the binomial is in this case quite close to a normal distribution. And then we say that, okay, under this hypothesis, we have a mean value of the binomials. This is p times n, which is here n/2. And we have a variance that's p1 minus pn, which is here n/4. That was the mean and variance of the binomial. And then we can compute probabilities using the normal distribution instead of the binomial, if you like. And in our example, this is more or less the same solution. We get a probability that's very close to what we get from the binomial calculation. Note that even though we here use a normal approximation, this is for the test statistic X. It's not for the sampling distribution of the data. So it's still a non-parametric test. It's a sign test. The only way we're using the normal here is to look up the p-values of our test. It's not for the sampling distribution of the data. So that's important to remember. Okay, this sign test is simple to do, but as you might notice, it only looks at the plus and minus. It doesn't care whether these samples that we had are just above 1.8, or if it's far above, or if it's just below or far below. So then we can come up with other tests that do not only look at the sign, but also care about the distance from this pre-specified median. One such test is the Wilcoxon test. Here we will require one more assumption, and this assumption is that we have a symmetric distribution. If we're willing to assume that the distribution is symmetric, we can get a better test that has higher power than the sign test. Since the distribution is symmetric, we have that the median is the same as the mean for this case. So instead of doing hypothesis tests on the median, we can say that it's now on the mean. It doesn't matter what we do. So the Wilcoxon test is based on looking at signs compared with this specified value, but also looking at the distance from this value. And it's sometimes called Wilcoxon rank test because it's formed by taking some ranks here and then the sign. So this is the rank and this is the sign of that rank. So I will present this statistic as an algorithm that you can go through to compute the Wilcoxon test statistic. And it's relatively straightforward to do this on a computer. It's all about sorting data and looking at the signs compared with the specified value. So let's go through this in steps. So the first step here is to look at the data compared with the pre-specified median. So we can compute something called VI, that is the sample minus this pre-specified median or mean. And then we also compute the absolute values of these statistics. So we look at the absolute values of these statistics. So this is done for all samples. And in step 3, we sort these distances from the pre-specified median. So here we sort these D1 up to Dn in increasing order. And in doing so, we keep track of their ranks. And the ranks is then from smallest to larger. So here we can say that this is D1 is the smaller one, and then D2, and then it continues up to the largest distance from the pre-specified median. So we sort these distances and keep track of their ranks, and then we can assign this rank 1, this rank 2, this rank n, because that's the biggest distance. And we also keep track of the sign. As we did in the sign test. So is this maybe a minus? Is this a plus? Is this a minus? And so on. And that's what we can call S1, S2, and so on up to Sn. So these are ranks and signs. So ranks and signs. That's what we have here. And then the final statistic that we can call W plus is then the sum over all data, and then we have the rank of that data, and then the sign of that rank. If it's a plus, we count it. If it's a minus, we ignore it. So here we can sum up all the ranks of plus, and then we can sum up all the ranks of minus. And as you might notice, they sum up. So if we just have this sum over I and ignore this indicator, we have the sum over I. So that would be such that the W minus here is the sum over all I, like this, minus V plus. And this sum over I is actually n plus 1/2, and then minus V plus. Rank sums for minus, rank sums for plus. So again, we need to compute a test on this. So we can now test, okay, are the means in line with the pre-specified value? Is the distribution here in line with what's specified in hypothesis H0? And it is possible to look this up in a table. So we can have a lookup table on the Wilcoxon distribution and find this hypothesis, conduct the hypothesis on W plus. But for not too small samples, it's again common to use a normal approximation. It's not a normal approximation on the samples, but it's a normal approximation on the statistic W plus. And what goes into this is again the expected values and the expected and the variances of these rank sums. In this case, not only the binomial, but now it's a rank sums. So here, for instance, for the mean, you see that this is okay. This is actually the sum like this, which is half, and then n plus 1 n over 2. So that's what we get for the mean. Because each rank under hypothesis H0 would be either plus or minus. So we get a half times this rank sum. And it's similar for the variance. Here we get actually the sum over I squared entering, and that's defined by this, but that's not 24. We divide instead by another number because we get half again and the variance. Okay, so given a normal approximation, one can do tests. So let's do this in an example. This is an example of a medicine taken by heroin addicts. And to check the effect of the medicine, they compare the scores on a test with the current value of 28 that is common for addicts. And the question is then, okay, when you take this medication, are you performing better than the usual score of 28? There are 14 data values, so n is equal to 14, and you see the data here. We can go through this and form the Wilcoxon statistics here. That's the plan. And I will do this in a matrix setting, and then now find the ranks of these compared with the mu tilde, which is 28. And I will find the signs of these and then compute the Wilcoxon test statistic. Okay, what is closest to 28 here, and what's the sign of this one? The closest to 28 is this one, which has just distance 1, and it's smaller than 28, so this has a minus. What's next? What's the second closest to 28? That's this one, and this is the distance 2, and it's also a minus. And then we continue like this, tracking away from 28 in a ranked order. Okay, what's the next in line? What's the third closest, and what's the distance? So this one is 6 away, and it's also a minus. This one is 7 away. Okay, so now I'm computing the distance. So this is what I call the V, and then this is the sign, and then we will here compute something called the ranks. I called the ranks I, didn't we? So now we're looking at distances. This is 1 minus minus. So they were the minus signs. This one is 15 above. This one is 17 above. This one is also 15 above. This one is 11 above. This one is 27 above, 27 above, 8 above, 15 above, and then this one is 25 above, and then 23 above. So you see there's a bunch of plus here, not so many minus. And in fact, the minus will have the shorter ranks, because here we see 1, this is the shortest rank, this is the next rank, then this is 3, 4, 5, there's 8 here, and then we get 11, 6, and then we have a draw with 15 here, 15 here, 15 here, so they can get scores 7, 8, 9. So we will just assign them all the same. So this is 8, the average score over these. And then the next one is 10, which is must be this one. And then 11, 12, and then they have a draw again. So this is 13 and 14. So they will get 13.5, 13.5. And based on this thing, we can now compute, say, W minus, which is the sum over all ranks, but the indicator for the sign should be minus. And there are only 4 minus, and they have scores 1 plus 2 plus 3 plus 4, which is 10. And I know that the sum over I from 1 to 14 is 14 times 15 divided by 2, which is 105. So that means that W plus must be 105 minus 10, which is 95. And this looks pretty extreme, doesn't it? We get some minus and we get some plus, but there are fewer minus. And not only are there fewer minus, they also get the very small rank. So that means they are close to the specified median of 28. Let's do the hypothesis test, and we will use the normal approximation to do so. So here we had this W value. What's the probability of observing something as extreme or extremer than 95? So this is, if we subtract the mean here, this is 52.5. And then if I compute this mean value, so this was 105 and then divided by 2. And then this is the square root of this expression, which is 14 times 15 times 29 divided on 24. And then this should be bigger than 95 minus 52.5. And then the square root again. Now we have normalized, so this value here is a standard normal. So this is the chance of a standard normal being larger than the expression to the right, which is 2.67. And this is far out in the tail of the Gaussian distribution. So if you might recall, this is 1.96, which gives a probability here of 0.025. And our value is even further. So here we would reject H0. The hypothesized value of the mean or median equal to 28 is not right. It seems like this medicine has an effect. The addicts score better in the test when they get the medicine. All right, this is the single sample Wilcoxon test or rank test. This can also be done for 2 samples, and that's how I motivated non-parametric statistics. We will now conduct 2 sample tests without doing the usual normal assumption on the samples. So we will not get a t-test here. We will get another test. And the test will again be based on ranks and signs. Now it's no longer signs according to a pre-specified mean or median. It's signs in the groups. So group 1, what ranks do they get? Group 2, what ranks do they get? Is it such that group 1 gets much smaller ranks in the sample than group 2? So this is what is done in the Wilcoxon 2 sample test. Non-parametric, no assumptions, just counting and ranking. Okay, the idea is that we pool samples. So here we have group 1, which we say is x1 up to xn1. And then we have group 2, which is y1 and then up to yn2. And we say that n is equal to n1 plus n2. That's the total number of samples. We will pool all these together and keep track of their ranks. So what we do is that we sort this vector of them all combined from smallest to largest. And in doing so, we keep track of the rank of group 1 and 2. So as an example here, we could say that, okay, which one is smaller here? Maybe we get, okay, this one is the smallest, x2, and what's the second in line? Maybe then we get this one, so that's yn2, and then we get x4, y2, and it continues, and the biggest is actually y3. So this is the order. This gets rank 1, this gets rank 2, this gets rank 3, rank 4, all the way up to this one, which it gets the best rank, it's the highest. We also keep track of the signs. So keep track of signs as well. So this one is from group 1, this one is from group 2, this one is from group 1, group 2, and so on, group 2. If it turns out that all these lower rank values have group 1 and all the higher ranked values have group 2, this is a clear indication that the groups are not from the same population. They have a different sampling distribution. If it's such that the ranks are about the same for group 1 and group 2, so that they spread out randomly, then it's natural to believe that the samples come from the same population. So then we could not reject a hypothesis saying that they come from the same distribution. That's the idea of the Wilcoxon 2 sample statistic. And it's based on a similar expression as in the usual one sample, single sample Wilcoxon test, except now we don't keep track of plus and minus, we keep track of groups 1 or 2. So here in this expression, W1 is the rank sum for group 1, rank sum for group 1. As we see, we find the ranks in the pooled sample, and then we take it when the sign is associated with group 1. We do exactly the same here for the rank sum for group 2. So here we find the ranks and then add it only if it's in group 2. So this can also be looked up, and we see that they sum to a known expression. So if one is big, the other is small. Instead of looking up in tables, it's again common to use a normal approximation for these statistics. And that's what we will do in an example. So here's our example. It's from ancient coins. And the question is if they have the same silver proportion. And we can call this one group 1 and this one group 2. And here in group 1, there are 7 samples, and in group 2, there are 8 samples. And we will check if it's the same silver proportion. So that means that could they be from the same population, or is it such that it changed over time? All right, so then should we go through this and give them ranks and sort them? So let's do so. We can order them from smallest to largest. So this is the rank ordering, and then we have the sign down here. So which one is the smallest here? This one is the smallest, so that's 5.1. And next in line, what's the second? That would have to be this one, 5.5. And then 5.6. And then this one, 5.7. Which one's next? 5.8. And then 5.9. 6. 6.2. 6.3. 6.4. And it continues like this, 6.5, 6.6, 6.8, 6.9, and 7.2. Those are the 15 samples, and they get ranks 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are the ranks sorted from smallest to largest in the pooled sample. And the signs, do we recall the signs of these values? So 1, we can just look at the newer coins. So this is from group 1, group 1, and group 1. And then 5.8 was also from group 1. 5.9 was from group 2. 6 was from group 1. Group 2, group 1, group 1. And then the rest are from group 2. So how many ones do we have here? 1, 2, 3, 4, 5, 6, 7, and that's what we should have. Okay, then we can compute the Wilcoxon statistic for these coins. We can look at the ranks and take the rank sum of 1. And perhaps we can just look at this here. How many ones do we have in the rank? Okay, we have 1 plus 2 plus 3. That's the 3 first. And then there's 5. And then there's 7. And then 9 and 10. And what do we get here? This is 37. So W1 is 37. Is this very large or is it small? It might appear small, does it? Because it seems like the ones get relatively small ranks, but then there are some ones higher up. And remember, there's one less in group 1, so perhaps it's natural that they don't spread out to the very top. Okay, let's do the hypothesis test using the normal assumption. And then we have to go through this statistic and normalize with the right numbers here. And in the end, we get the probability of observing something this small or smaller, which is 0.014. So it is quite small. It's likely not random variation. So this means that we should reject H0. W1 is too small. So then we reject H0. They are not from the same population. The newer coins have less silver than the older ones. That's or it seems at least. There's evidence for this. We can extend this test for 2 samples, 2 more samples, then it's called Kruskal-Wallis test. This is in many ways similar to the basic steps of analysis of variance in the case of a parametric model where we assume Gaussian samples for the data. The Kruskal-Wallis test is a non-parametric test, so it does not conduct any kind of parametric assumption, and it extends the Wilcoxon test. So the idea is again to pool samples and then find ranks. So here we say that we have Xij, where I is 1 up to k groups, and for each group we have n I samples, and we say that n in total is all the sample measurements. The way it works is again to form a pooled sample of all the data x11 up to x1n1, x21 up to x2n2, and so on up to xknk. And then we sort this sample, this pooled sample, and we keep track of ranks. And we keep track of group index. And we then get ranks here in the end. So we get ranks for, say, group 1, for group 1, we get ranks R11. What rank does that get? This sample get in the order? What rank does the second sample get in the order, and so on? These are the ranks of the n samples. And then we can average these or sum them together in some way. So we'll say that the R1 is then the sum of these ranks. J. And this does not only hold for group 1, it holds for other groups as well. So instead of having the group 1 here, I can say for group I have this one. And then this holds for I equal 1 up to k. Naturally, if some of these ranks are much higher than others, it indicates that this group has bigger response variables than some other groups. And that's what goes into the Kruskal-Wallis test statistic. Age is formed, as we see, by these group ranks squared and then normalized by the number of samples in that group. Under the hypothesis H0 that all groups have identical distributions, this is approximately a chi-square distribution with k minus 1 degrees of freedom. And this makes it possible to do hypothesis tests, which we can do in one example. Here's an example with 3 groups. So k is equal to 3, and n1 has 5, n2 has 6, and n3 has 8 samples. The question is if the missile systems are different, so that these burning rates differ between groups. And when we looked at analysis of variance, we compared the variance within groups and the variance between groups. Instead, for these Kruskal-Wallis non-parametric tests, we look at the differences in the ranks in a sorted order of all data. And this is done here in the table. We look at all samples and check their ranks. The ranks for the first group are 1, and then it's shared with this one 9.5, and these other ranks, and in total we get 61. For the second group, we have ranks 4, 5, 6, which are rather small, but then there are also some bigger ranks here, and we get 63. Or 3, the third group, have a few small ones, but then it also spreads out with some higher ranks and gets 65. And if we go through this calculation, putting in these ranks and n, which is the sum over all these ni, 5, 6, and 8, we here get an observation of a equal to 12 divided by 19 times 20. And then in the sum, we get 61 squared over 5 plus 63.5 squared over 6 plus 65 and a half squared over 8. And then we have to subtract 3 times 20. I got 1.66 here, which is a small value. If we look at the chi-square distribution as a density function, it looks something like this. And the chi-square to 0.95 percentile is 5.99, which means that this is the rejection region for the hypothesis, and we end up somewhere here with 1.66. So here we do not reject the hypothesis. We say that, okay, actually it seems like they all come from the same population. There's they can maybe be pooled together. There's no difference between the missile systems. That's a short introduction to non-parametric statistics. Thank you very much.